This is the fifth and final podcast in gas calculations. Here we're looking at the moles and the pressure and the temperature and the volume of the gas, and what we're going to arrive at is known as the ideal gas law. A few facts. The volume of a gas is proportional to the amount of gas in a container. And here you will notice that the volume will increase if the pressure and temperature are constant as we add more gas. So if we have twice as many moles of gas, we have twice the volume. If we have 3 times as many moles of gas, we have 3 times the volume. In every case, the mass on top of the piston is the same. The particles are all moving with the same velocity. Pressure and temperature are constant. As the moles went up, the volume went up. It turns out that pressure is proportional to the amount of gas in the container. As more gas is added, the pressure increases if both the volume and temperature remain constant. Notice that on the left we have 3 moles of gas and a pressure of 10, while on the right, to maintain the same pressure and temperature, we have to have 6 moles of gas because the pressure has also doubled. The same is true if you are going to increase or decrease the temperature of a gas. If we cool this gas, you notice that we have 3 moles of gas on the left and a pressure and volume of 10. But if we have lowered the temperature of the gas, cutting it in half, we need twice the molecules in order to maintain the same volume at a pressure of 10. The more gas is added, you have to cool the gas container to maintain both a constant pressure and volume. When you put all of this together, we come up with what we call the ideal gas law, because pressure times volume over temperature is proportional to the moles of gas. And as you may remember, you can remove a proportionality by making it equal to the moles times a constant. The constant we use in chemistry is known as the universal gas constant. We give it the variable R, and we rewrite this equation like the ideal gas law, PV equals nRT. This is an equation you should know. You will be using it more than once. To use it, we have to make sure that we have our pressures, volumes, temperatures, and moles all in the right units, because R has different values in units depending upon what you are using. If, for example, pressure is measured in atmospheres, we would have R in liter atmospheres per mole K. There are other values for it that you will come across in future usages. Let's take a look at a sample problem. How many moles of nitrogen gas is required to fill a small room with a volume of 960 cubic feet, fortunately converted to 27,000 liters, to 745 millimeters of mercury at 25 degrees C? Well, the first thing we need to do is be sure all of our data is in the proper units. The volume is 2.7 times 10 to the 4th liters. The temperature is 25 plus 273, or 298 kelvins. And the pressure is 745 millimeters of mercury times 1 atmosphere over 760 millimeters of mercury, the value of a standard atmosphere. And we have 0.98 atmospheres. And R in this particular case will be 0.0821 liter atmospheres per mole K, since our volume's in liter, our temperature is always in Kelvin, and here our pressure is in atmospheres. So to solve the problem now, we plug the values in. First thing, of course, we need to do is a little bit of algebra, and you'll find that you can rearrange the equation, and we have PV over RT equal to N. Now all you do is substitute, making sure that when you are doing the arithmetic, you pay attention to the order of operations using your calculator, and do the top, and then use parentheses if you're going to divide the bottom. And that way you will arrive at your answer of 1.1 times 10 to the 3rd, or about 1,100 moles, which in the case of nitrogen would correspond to about 30 kilograms, that you would of course get by multiplying by the molar mass of 28 grams in a mole. And that is an example of using the ideal gas law to determine the number of moles of gas in a particular sample. something very useful in stoichiometry.